Mining has long been thought to have a relatively insignificant impact on biodiversity compared to other larger land uses. This is evident in the literature, with less than 1% of papers published in top journals referring both to mining and biodiversity. Mining does, however, have a wide range of impacts on biodiversity. For example, there are site-related impacts such as vegetation clearing and habitat fragmentation, as well as a wide range of types of soil damage. Additionally, there are also many long-distance impacts associated with mining as well, such as water pollution, air pollution, and noise pollution. Additionally, many of these impacts are irreversible, with some lasting hundreds of years. With this in mind, the aims of this study were to investigate the impacts of mining activities on the biodiversity of South African grasslands. Despite mining activities occupying a much smaller area than many other land uses, it is important to understand the threat mining activities pose to grassland biodiversity due to the density of mining activities in the grasslands. Additionally, 35% of the biome is already transformed, with less than 3% under formal protection, leading to the grasslands being classified as a critically endangered biome and the South African biome most urgently in need of conservation. Hence, the first objective of this study was to determine if mines have a disproportionate proximity to grassland biodiversity priority zones. For this, we first extracted the surface footprint of mining activities from the National Land Cover Map, then limited its extent to the grasslands. Despite the fact that underground structures of mines also have a significant impact on biodiversity, we could not include them in here due to data availability. Next, we defined grassland biodiversity zones based on the protected areas, important bird areas, and wetlands of the grasslands, due to their varied contributions to conservation, biodiversity, and sensitivity to the biodiversity impacts of mining activities. As mentioned previously, many of the impacts of mining activities can extend beyond the boundaries of mine sites. The distance of these biodiversity impacts on mining activities vary. Hence, the previous studies have often generalized the maximum distance of many of these impacts together at between a maximum of 5 and 10 kilometers. Therefore, we created buffers of 0 to 1, 1 to 5, and 5 to 10 kilometers around these biodiversity priority boundaries. That is, the protected areas, important bird areas, and wetlands. This then allowed us to determine the observed mining area based on the National Land Cover Map within each of these biodiversity zones and their representative buffers. We then randomized the location and orientation of the same polygons representing mines in the 2018 National Land Cover Map in order to represent the expected mine area within the biodiversity priority zones and their buffers if mines were randomly orientated and dispersed throughout the grasslands. This randomization was repeated 1,000 times, allowing us to compare the observed and the expected mine area within the biodiversity priority zones. The second objective of the study was to determine if grassland vegetation types with higher conservation values have more mining area. In other words, if there is disproportionate mining in more biodiverse vegetation types. However, there are multiple challenges when trying to obtain conservation values and measures of biodiversity of the grassland vegetapes of South Africa. However, previous studies have shown that endemic species richness serves as an appropriate index for both conservation value and overall biodiversity. Hence, we extracted a list of the species endemic to each vegetation type from the vegetation map of South Africa by Musina et al. These endemic species were then scored between 1 and 7 based on their IUCN Red List status, with least concerned species receiving a score of 1 and near extinct species receiving a score of 7. This allowed us to give a higher conservation score to vegetation types with more threatened endemic species. Lastly, we determined the remaining natural extent of each vegetation type. All of this information was then combined to create the raw, red list weighted endemic species richness per 100 square kilometers remaining natural extent for each of the vegetation types. The first important result to note is that each of the biodiversity priority zones show different patterns of mine establishments surrounding their boundaries. This figure shows the difference between the observed mine area, illustrated by this red square, and the box plot representing the expected mine area within protected areas and the surrounding buffers. The asterisk indicates a significant difference between the observed mine area and the expected for that respective buffer. First, we found that 44.8% of mines are within 10 kilometers of protected areas. However, the observed mine area within and within a 0 to 1 kilometer buffer surrounding protected areas was significantly lower than expected, whilst it was higher within a 1 to 5 and 5 to 10 buffer surrounding protected areas. This lower mine area closer to protected areas suggests that the boundary effect of mining activities on surrounding biodiversity is considered. This is quite likely due to legislation in place in the National Protected Areas Act, accounting for the buffer zones surrounding protected areas. However, these results also support previous findings, which suggest that the long distance impacts of mining are often ignored and underestimated. Additionally, whilst the mining area within protected areas is lower than expected, the presence of mines within protected areas, as illustrated in these cases, is still a major cause for concern, as according to legislation, there should be theoretically no mining area within protected areas. Yet, in the study, we found mines in 99 legally designated protected areas, the majority of them declared nature reserves. There are multiple potential reasons for this, such as inaccuracies in the relevant databases or past inaccuracies in documentation of protected area boundaries. Though probably accounting for very few of these observed cases, some might also be as a result of PAD. This is where protected areas lose their status, or some or even all of the area, often to allow lucrative mineral extraction within this area, some cases of which have already been observed in South Africa. The observed mining area with important bird areas and all their surrounding buffers was lower than expected. One potential reason for this is the fact that important bird areas were first identified in 1998, by which time many of the mines in South African grasslands were already established, thus naturally already pushing the important bird areas further away from these sites. Alternatively, it is possible that the same characteristics that are given high priority in important bird area designation are also taken into consideration during land use planning regarding mines. Regardless, this potentially means that important bird areas are less likely to be disproportionately impacted by both the short and long distance impacts of mining activities. This is fortunate given the proven sensitivity of bird communities to the impacts of mining activities. Despite the fact that the observed mining area was lower than expected within wetlands and within a 1 to 5 and 5 to 10 kilometer buffer surrounding wetland areas, 96.8% of mines were within 10 kilometers of the grassland wetland areas, explained potentially by the high disproportionate mining area within a 0 to 5 kilometer buffer surrounding wetlands. There are multiple potential reasons for this, but some of these include the underlying geology of wetland areas and the mineral deposits, as well as the high water dependency of many mining activities. Conversely, there are two factors could also explain the low mining area within a 1 to 5 and 5 to 10 kilometer buffer surrounding wetlands. Despite the mining area within wetlands being lower than expected, this is still cause for concern given the severe water pollution risk from mines and the long distance at which these impacts can affect biodiversity, especially when compared with the very high mine area adjacent to wetlands. Lastly, we found that there was no correlation between the conservation value within a vegetation type and the actual mining area within a vegetation type, thus suggesting that there is, at least at the vegetation type scale, no disproportionate mining within vegetation types with higher conservation values, as defined in this study. In conclusion, conservation and land use planning has largely focused on the direct impacts of larger land use types, such as agriculture and forestry, and to a lesser extent due to its smaller area mining. However, in this study we show that biodiversity priority zones are actually at a disproportionate risk from the long-distance impacts of mining activities, supporting the idea that there is serious need for better understanding of the long-distance impact of mining activities, which has often been lacking due to the strict regulation around access to mine sites, stunting such research. Hence, this study justifies the growing concern in literature and policy regarding the often ignored and underestimated long-distance impacts of mining activities. Thank you for your attention and time, and a special thanks to my funders. If there are any questions, I would be very happy to answer them. Thank you very much.